In this video we'll look at linear transformations and how they apply to vectors and matrices. First up we have our knowledge of functions such that for any value of x that you substitute into an equation you get a y coordinate. So we have a graph here of y equals sine x. That we know is a function because it also passes what we call the vertical line test, because every single point on this function here will have unique values of x for any given value of y. As opposed to this equation here, if you were to draw the vertical line, it passes through 2 points with the same value of x, so x is not unique. So that was one definition of functions. Now in terms of vectors, we consider a function whereby we map one vector onto another using some transformation. So here w is the image of vector v, and we are transforming it using some method of t. So w is equal to some transformation of vector v. So I suppose we have vector v is xy, so w, the image, is some transformation of v. In this case it's equal to y x plus y, which means that the y value here occurs at the top and the base number here is the sum of these two terms. So 1, 3, if we transform that, the 3 remains the value at the top here, so the y value, which is 3, and then the base value here is x plus y, which in this case is 1 plus 3, we get 4. So if we were to look at the next one, then if I transform this vector under our transformation, then the value we have up here will be 4, and the value here will be x plus y, which is going to be 4 plus negative 1, which is going to be 3. Now, these are linear transformations if they satisfy two properties, the addition property. So if I transform u plus v, so I'm adding the two vectors first and then transform it, that is the same as the individual transformations summed. Likewise, if I were to transform a multiple of u, that be the same as my multiple of the transformed version of u. That would imply we have linear transformations. And as we head down here, generally this expression here doesn't involve higher powers, and if it does, it's likely not to be linear. In this problem here, we want to show by counterexample that this transformation, whereby xy becomes xy squared, is not in fact linear. So to do this, we will, by example, so by choosing values for u and v. So remember that if it is linear, then if you transform the sum of your two vectors, that is equal to the transformed first vector plus the transformed second vector. So if I were to let u equal, say, 1, 2, and v equal, let's make it 3, 4, then the left hand side of this expression here, I'm going to transform u plus v. So let's add those together and I get 4, 6. So if I transform that using this transformation up here, x remains x, so I end up with 4, and I end up with y squared, which is going to be 36. Now the right hand side of this transforming u, so I'm transforming that under this transformation, that will be 1, and then y squared is 4. Now I'm adding the transformation of v, which is 3, 16. And if I add those together, I'll get 4, 20. So in this case, left hand side does not equal right hand side, therefore it's not a linear transformation. Alright, so now looking at geometric linear transformations. Now this is where we start to apply things to our matrices. So point P, x, y, the P dash is the image, x dash, y dash. So we are transforming one point into another under this transformation. X dash is equal to A times X plus B times Y, etc. So we can express that there as a matrix equation where X dash Y dash, a 2 by 1 matrix, is equal to the coefficients A, B, C, D. That will in fact be our transformation matrix multiplied by X, Y. So in this case, in shorthand notation, V dash is the image is equal to some matrix A multiplied by the original values of X and Y. In this example, we'll look at how this equation here will transform both a point and a line. So for the first one, in part A, we've got the point 3, 2, which is in fact x, y, and that is going to become, under our transformation, a new point, x dash, y dash. So this here will work out x dash, y dash if I know x and y. So I know that x dash is equal to 3 times by x, which is 3, minus 1 times by y, which is 2. So I get 9 take 2, which is 7. My y dash value is going to be x plus y, which in this case is going to be 3 plus 2, which is 5. So therefore my point 3, 2 under our transformation has become the point x dash y dash, which is now 7, 5. So if we know x and y, we can substitute in here. In part B here, we don't have any particular values. We do have a function. So I need to work out what x is equal to and y is equal to from this equation here. So I need to rearrange this to solve for x, y. So let's write that as a matrix equation first, which is what we have here. So now I need to solve for x and y. So I'm going to multiply to the left here by the inverse of this 2 by 2, and likewise multiply here by that same inverse, which gives us this. So now, if I were to work out x, y, the matrix, 2 by 1 matrix, I've got the determinant is going to be 3 take negative 1, so I have 1 on 4. Then I swap this diagonal here, so the 1 and 3, and I change the sign on this diagonal, so 1 and negative 1, and that's multiplying by x dash, y dash. And if I expand that, I'll end up with x, y equaling this matrix. So I can now substitute in here my values of x and y using these in terms of x dash and y dash. So now y equals 2x take 1 will become this equation here, replacing y in terms of x dash, y dash, and likewise x in terms of the same variables. And we can simplify that, and that will give us, which we can then multiply by 4 to simplify, then rearrange to make y dash the subject, and then we can finalize it by writing it up neatly. So y equals 2x take 1, the original function has been transformed into y equals 3x take 4. And we can see here that the original function y equals 2x take 1, this function here, under this transformation has become 3x take 4.